make an assumption.
Yeah.
Yeah, what about you?
Not really.
Not this weekend?
Not this weekend or next weekend as far as I know. Chilling where I can.
All right, so we're going to do this problem for the homework, and then we'll finish up this section and start PFD. Welcome back.
You're going to Mexico.
You got me
After
set.
happened with the cartel here, your dumbass is still going to Mexico.
Somehow.
Oh, I thought you were for real. I'm like, brother.
So the first thing we want to do is make that a 1
Have you seen that though?
right here.
Let's still go to Mexico.
We always want a sum of squares or a difference of squares with a 1. So we're going to factor out the 144.
Yeah, it really gets weird.
We can factor out the 7 also. And when we factor out the 144, the power has to come with it. So if it was a square root, it would be a square root of 144. If it's a square comes with it. So whatever the power is there has to come with it. And when we pull that 144 out, we have 1 plus. There is no 144 here, so it puts a 144 there. And then maybe we'll get some cancellation, so we don't need to multiply that out yet. And then this quantity we want to write as a square. So we'll write that as x divided by 12 squared. So that is our setup. Is that okay with everyone?
That makes more sense.
Makes some sense?
That makes more sense.
Makes more, is this where your error was?
Oh, we're already deep.
Well
in.
past the error?
Yeah, we're deep in already.
Sine, secant, or tangent?
Tangent.
Tangent because it's a plus. So tangent will equal, well, we usually write the x on the left. So x over 12 will equal tangent. And now we have 1/12 dx will be secant squared of theta d theta. And our whole goal is that right here, if we have 1 plus tangent squared, that will reduce to secant squared. That's our goal. Just collapse that denominator. So x is 12 tan theta, so we have to square 12 tan theta. Dx is 12 secant squared. This is 1 plus tan squared, quantity squared. This 12 squared right here is going to be a 144, which will cancel one of those. I'll factor that 12 out, and we can cancel some more here. Then we have tan squared, secant squared. secant to the fourth. So I'll stop there and let you finish it off if you haven't done this one yet. At this stage, you have a couple of choices. This is an even power on tangent, so we can't use that special pull a secant tangent off thing. And if we can't use one of those rules for products of powers, we have two choices. Turn everything to sine and cosine, or use a Pythagorean identity on the numerator. So we could write that as secant squared minus 1 and then split the fraction. So try that one out, and if you get stuck on that, we can go over it again on Tuesday and finish it. Any questions up to that point? Okay. So here's where we are. Same first step. We want a sum or difference of squares with a 1, a leading or trailing 1. So our target out of the gate is that. We want that to be a 1. So we're factoring the 64 through a square root, so that square root comes with the 64. So that's going to come out as a 1/8. And there is no 64 here, so you can think of it either as putting a 64 in the denominator when it comes out, or you can think of this as 64 over 64. So when you factor out the 64, you're left with x squared over 64, which is x divided by 8 quantity squared, minus 1. And then sine, secant, or tangent. Secant. So sum of squares, tangent. Difference of squares, sine or secant. When it's a trailing 1, it's always going to be secant, because secant squared minus 1 is tangent squared. 1 minus sine squared is cosine squared. So x divided by 8 will be secant of theta. And then we take the derivative. Dx in the numerator. If we look down here and multiply both sides by 8, we're going to get 8 sectan in the numerator. And down below, secant squared minus 1. So this becomes and that's square root of tangent squared. If there were no limits of integration, we would just instantly say square root of tan squared is tangent. But because there are limits of integration, we have to just make sure that they've put us in the right quadrant, that square root of tan squared is tangent and not negative tangent. So when we look at these limits here, these are all positive, and if we come down here to check what quadrant theta is in, let's look at 16. We'd have secant of theta equals 2, which means cosine of theta is equal to 1/2. So that's putting us in, this is going to put us in quadrant 1. And in quadrant 1, tangent is positive. So the square root of tangent squared is tangent. We don't have anything, nothing fishy going on. So square root of tangent squared is tangent, and that's going to cancel with the tangent in the numerator. And all we have left inside then is that secant. And we've seen earlier that the integral of secant is natural log absolute secant plus tangent. And no plus c because we have limits. Now we go to the triangle that's going to take us back to x's. Sorry. Way that relates x and theta. And so if we look at this, we want that to be true with that triangle. So we create sides to make this true. And secant is hypotenuse over adjacent. It's the reciprocal of cosine. And this makes the unknown side the square root of the hypotenuse squared minus the other side squared. So secant of theta is x over 8, or you can look at the triangle. Tangent of theta, opposite over adjacent. Then we go back to the x limits. Any questions up to there? Okay, so we plug in the upper limit. Plug in the 16 there. And we get 256 minus 64. So 256 minus 64. So that 100 minus 8, I think. So square root of 92. 8. Less.
No, I think 192.
Possibly, yes, thank you. And then close it, and then subtract natural log, plug in the 8 root 2, so we'll get root 2. And then in here, we're gonna get 64 times 2, so we're gonna get 128 when we square this. Minus 64 is 64, square root of 64 is 8, 8 over 8 is 1. So we get that. This looks like there's probably a perfect square in it, but I can't think straight right now. Does 4 go into that?
It ends up being like 8 red 3. So there's something like that.
Okay, so 8 root 3 you said?
Yeah.
So we'll get this. And you could leave it like that. Most of the time the book will give you a combination though. They're going to use a log property and write it like that. We don't need the absolute value because everything's positive. So log of A divided by B is log of A minus log of B. And we just did that backwards. So, and this thing became 64 times 3. And so the square root of 64 was 8, which is how we got the 8 out in front.
Would the answer be in absolute values bars still, or no?
This is positive and this is positive, so we
Oh, they're
don't
just
need
numbers.
them.
Okay. Yeah.
So you could put them, and that's totally fine. We just don't need them because everything in there is positive. Any other questions on it? Okay. So now we're going to mix it up a little bit. This denominator is not factorable. In the next section, what we're going to see is if we do have a factorable denominator, we can use this technique called partial fraction decomposition and break it apart. But this is not factorable, so if we ever have a denominator that's a quadratic that's not factorable, we complete the square. So we've done this before. So let's do it again. What is the constant that we need for these first two terms to have? What constant do they need to have to complete the square? I heard a 9. We take the coefficient of x, divide by 2, and then square it. So negative 6 divided by 2 is negative 3. We square it, we get a 9. So we want a 9, so we put a 9 in. And then we can think of just taking that 9 from this 34, so that these two constants add up to that. We've just partitioned 34 so that part of it's going to go over to that perfect square. And so then this is x minus 3, quantity squared plus 25. Sum of squares. I'd like it to be a sum of squares with a 1, not a 25, so I'm going to factor 25 out. There's no power, so it comes out as a 25. Now once again, you don't have to, but if you need to, multiply this by 1, so it's, if it makes it clearer to you how we do the factorization. Then we want that first term as a single square. So now we have a sum of squares with the trailing one. Now this is in arctangent form. We already know, one of the integrals we know is that dx over x squared plus 1 integrates immediately to arctan of x. The only change is that this is a modified x, but it's a linear modification of x. So we can integrate to arctan and then use reverse chain rule. So let's do that. So this is going to be 1/25. I'm going to leave a little space for the reverse chain rule. This will be inverse tangent of x minus 3 divided by 5 plus a constant. And what is the derivative of that? 1/5. And if you want, an easy way to think about why that is, you have x divided by 3 over 5. If you divide the 5, if you split the fraction, you get that. So the derivative is the coefficient of x, 1/5. So we're going to divide this by 1/5, which means multiply by 5 over 1. So this is from RCR. So our final answer, all we have to do is simplify those constants. And we'd have that. Now, if you didn't notice that it was in the arctangent form, and you're in the habit because you're in the section with trig sub, which sub would you use if you wanted to go trig sub?
Tangent.
Tangent. So, or if you didn't notice that, you would say this. And then you would take the derivative of both sides. And then you would do your substitution. Is it 1/25? Now when you do your substitution, the dx in the numerator will be 5 secant squared of theta. Theta, and the denominator will be tan squared plus 1. But what is tan squared plus 1? Secant squared. So this denominator cancels with that. So this would all become 1/5, the 5 factors out to the front, integral of d theta. Well, that is just 1/5 theta plus c. And then we come back over here. If we wanted to isolate theta, theta is arctan of x minus 3 over 5. If we move a function to the other side, we use its inverse. And of course, we end up with the exact same answer. So if you forget your basic inverse antiderivatives and you just use trig sub, it's going to come out in the wash anyway. So if you're going to remember one thing between the arc integrals and trig sub, remember trig sub, because it takes care of all the basic inverse integrals. All right, any questions on any of those steps? So if you don't recognize this as basic inverse tangent or basic inverse sine or basic inverse secant, in all those cases, you're going to end up with this integral of just d theta if you do trig sub. So if you do get to the integral of d theta, just go back and look and say, oh, what did I miss? Because you could have done it directly. Okay. You all try this one, completing the square. Factor out that 2 in the denominator first. You can't complete the square without a 1 as the coefficient of x squared. So to complete the square, you have to have a leading coefficient of 1.
Yeah, but when you're factoring out, when you're completing the square here, you're going to get x minus 6x, so you're going to get 9. When you pull 9 out of 36, you get 20. So that's the difference. This is they just need a different constant.
So that's what you should have got after you completed the square. Divide the 6 by 2 and square it and you get 9. So we need 9 from this 18, so I'm going to separate the 18 into 9 plus 9. And then then this part is a perfect square trinomial,
6.
which factors into that. Now we have sum of squares, but not sum of squares with a 1. So to force it to be sum of squares with a 1, we want to factor out that 9. So that's going to give us 1/18. And there is no 9 here, but you can make one there, so that your factorization takes that 9 and mashes it with the 2 out in front. So we end up with x minus 3 over 3, quantity squared, plus 1. Once again, that's in arctan form perfectly. So we can go directly to the antiderivative. And if you didn't recognize it, you could go trig sub with tangent and you would get there quickly. So let's go arctan now. This will be arctan of x minus 3 over 3. And what is the derivative of this? 1/3. So we have to divide by 1/3, which is the same thing as multiplying by 3 over 1. And so our final answer is this. Did it work? Inverse trig is one of those, or trig sub is one of those things you just have to do a few or a bunch of practice problems. Question on that one, or you good? Good on that one? Yeah, I see smiling faces. This is weird. Okay. Maybe it's because I can't talk as much. 8.5. This is a section you will like, most likely, because it's an easier section and it's very prescriptive. There's not a lot of big thinking going on, which is great. We're going to go small ball thinking. So notice these two functions are equal. And in algebra, you've gone this way a million times. All right, you'd multiply this one by x plus 4 over x plus 4, multiply this one by x minus 2 over x minus 2, you'd get a common denominator. And you would take two rational functions and merge them into one. You haven't gone the other way. But notice, if you could go the other way, isn't this a lot easier to integrate than that? If you could, this is a factorable denominator. This denominator will factor into x minus 2 and x plus 4. And if you could factor it, then this is simple, right? These are both in log form. So you get natural log of x minus 2 in absolute, and then 2 times that. So 2 times natural log absolute x plus 4 plus c. So if we can figure out the algebra that takes us this way, that'll make our life easier. So this technique is called PFD, partial fraction decomposition. We're going to think of these little fractions as partial fractions of this bigger combined fraction. So we want to take our big rational function and break it into little fractions. So those are the partial fractions. And here's how we do it. So we do it like that. This looks way more complicated than it is. I want to highlight a couple of things. Let's just imagine our denominator factoring into two pieces, just like on that last one, then this would be our PFD right here. That would be our PFD, just these two terms. So however many factors you have, that's how many terms you end up with. So if we only have two factors, we end up with two terms. Okay, so here's what that means right there. The cool thing, once it's factored, I'm going to take the integrand out. I'm just trying to rewrite this big fraction as two little fractions. So what this is saying is that this has to be broken apart. The decomposition is going to be found by taking each of the factors and creating a fraction with matching denominators. Denominator that matches this factor, denominator that matches this factor, and the numerators are just constants. So I'm going to use A and B. You could subscript if you want, but subscripts are a pain in the neck unless you have to use them. So if we only have a few, A, B, C, D, E, or something, we'll just use capital letters. You could use A sub 1, A sub 2, A sub 3, A sub 4, but... Okay, so there is our PFD. We've partially decomposed it. Now we need to find A and B. So what we're going to do is multiply, we're going to clear the fraction. We're going to multiply both sides by this denominator on the left. So we're going to multiply both sides by that. Let me move this over. So we're going to multiply this side by x minus 2 times x plus 6. And then we're going to multiply this whole side by the same thing. On the left side, you just get 8. Right? You multiply by that denominator so they cancel. Right? That's our strategy. Clear the fraction. So that's canceling with that. On the right side, this quantity needs to be shared. It has to go across, distributed. And do you see that when it distributes to the A, we're going to have a denominator of x minus 2 cancel with the x minus 2 in the top. So we'll be left with, so that's going to come across, we're going to be left with A times x plus 6 and B times x minus 2. Good? Okay. So this whole green blob is coming to the A, coming to the B. The x minus 2's cancel there. The x plus 6's cancel there. So we've cleared the fractions by multiplying by the least common denominator. This is linear. We can solve it. I know we can. So here's what we're going to do next. There's two techniques at this stage. We're going to learn the traditional technique first. So we distribute the A, distribute the B, and I'm going to group the like terms together. So the yellows are linear. Those are the x terms. Let me just write it down here. I'll go underneath. So this is going to be A plus B multiplied by x, the linear terms, the x, where there's the variable of just x. And then I'm going to group the constants together. 6a minus 2b. On the left side of the equation, I'm just going to think of that as a polynomial that's got no x's. And now if I ask you this question, all of you will answer the same thing, I know. What is A?
3.
3. No tricks. What is B? What is C? -1. If you have two polynomials that are equal, that can only happen if the corresponding coefficients match. We have a polynomial on the left. We have a polynomial on the right. The only way that that can happen is if the coefficients match. So let's get that out of the way. So this tells us that a plus b, coefficient of x, right there, coefficient of x, has to match the coefficient of x over there. So a plus b must be 0. Similarly, 8 must be equal to that constant. It's the only way that these two polynomials can be equal. So we're going to have 6a minus 2b equals 8. And with that second equation, we can, of course, divide out the 2. That'll make it a little bit easier. So back to algebra. Now we have a system. What can we do to those two equations to eliminate one of the letters? If we add them, if we come through and just add these, let's just add. If we add, we get 4a. How many b? None. So this tells us that a is 1. And then we plug it back into either equation, and b has to be, we plug a equals 1 in there, subtract it over, so we get b is -1. And you can plug your a into either equation. Doesn't matter. So here's where we are. We now have the integral of, let's see, let me go back up there a second. So right here, we took the inside of the integral, and we're rewriting it as a divided by and b divided by. We have a is 1. So it's going to be 1 over x plus x minus 2. b is -1, so we're going to get -1 over x plus 6. So we've now decomposed the rational function into its partial fractions. And then this, we can integrate easily. Natural log absolute x minus 2 minus natural log absolute x plus 6 plus c. And if we wanted to be fancy, we could combine these. Here we would need to leave the absolute values because there's no guarantee that what's inside is positive. So that is a very basic PFD. Two linear factors in the denominator. Let's do another one. This one came with a factored denominator. So remember, we have to have a factored denominator to do PFD. Most of the time, it's not going to come with a factored denominator, and we have to do that work. So when we look here, this is going to factor, and we can factor it all the way down. factors. So how many partial fractions are we going to have? 3. We're going to have 3. So we're going to take the inside we're going to rewrite it as a divided by x plus b divided by x minus 1 plus c divided by x plus 1. And now we multiply both sides by this denominator. When we multiply the left side by that denominator, we get the numerator. When we multiply it by the right side, one of the x's cancels, so we'll be left with x minus 1 and x plus 1. So a times x minus 1 times x plus 1. Does everybody see that? So we're taking this factored denominator right there. There it is factored. Multiply it by the first term, the x's cancel. Now we take it and multiply it by the second term, and the x minus 1s will cancel. We'll get a times x plus 1. And then when we
be b?
b, thank you. And when we multiply it by the third one, we'll get c times x minus 1. So we're multiplying the entire equation, multiply it by x times x minus 1 times x plus 1. So on the right side, we have to expand all this. So this is going to be a times x squared minus 1 plus bx squared plus bx plus cx squared minus cx. And this first term will be ax squared minus a. And we add all this stuff to it. Oh, not that. Not that. And then we're going to group all the like terms. So we have a plus b plus c times x squared. So we're taking the 3 squares. And then we're going to take the linears there and there. So we'll have plus b minus c times x. And then there's only the one constant right there. And then the left side, we have 4x minus 2. But we need an x squared term, so we just drop in a placeholder like that. And now we have 2 quadratics that are equal to each other. The only way 2 quadratics can be equal to each other is if the corresponding coefficients match. So this has to be true. Those have to all match. So this will build a system. So the system that we get is 0 will equal a plus b plus c. So there's our system. Right away, we can solve for A. A will be 2. So we can then rewrite our system, plugging in the 2 back up here. So we can plug the 2 in there, and I'm going to move it to the left side and make it -2. So I have -2 equals B plus C, and then 4 equals B minus C. So this 2 is going in there, but then we're moving it to the other side of the equal sign. We'll add these together. -2 plus 4. B plus B is 2B. C minus C is 0. So we get that B is 1. And if B is 1, in either of these equations, what is C? -3. So now we've solved the system. Now we have. So we are at the integral of A over X, and A was 2. And then B over X minus 1. So B is 1. C is negative. So and then C over X plus 1. C is -3, so we'll have this. And each of those integrates to a log. You can do some log properties if you want, but we don't have to. All right. Any part of that you're not tracking? Okay. So, the next step up is this, where we have a factorization that includes a repeated linear factor. And what this says up here is that if you have a repeated linear factor, you need a partial fraction for each of the powers. So right down here, if we take our inside, we need a partial fraction for the a for the x minus 6. And now we're dealing with our repeated factor. We're going to need a partial fraction for that factor to the 1 and a separate partial fraction for the power of 2. If this was a power of 4, we would have 2 more, an x plus 2 cubed and an x plus 2 to the 4th. So whatever that number is right there, that exponent, that's going to tell you how many partial fractions you have.
Why wouldn't you just have 2 fractions of the without the exponent? Why does it have to be partial fractions with the exponent?
So if we want to build this sum back to here, we need to have a 2 as a power in the denominator somewhere to build it up. So if we just had these two and you multiply top and bottom by the corresponding denominators, you're not going to build up to an x plus 2 squared. So we need to have, especially the highest power here, so that we can get back to that when we create our least common denominator.
Yeah, my main thing is like, when I was thinking about this logically, my first instinct would just be 2 fractions of x plus 2 in the denominator. I wouldn't think to have an x plus 2 squared.
Right. And so we do it this way because it works. And if you start to try it, if you try it without that square, you're not going to be able to create a square. So we need one for each of the power. If this was a 4, we need to go all the way up to 4 to ensure that we get a power of 4 on that factor in the denominator. Now we're going to multiply both sides by the denominator on the left. You start to do this sort of quickly. This gets multiplied across, and you cancel the x minus 6. This gets multiplied across, and you cancel 1 x minus 2, x plus 2. This gets multiplied over here, and the x plus 2 squareds cancel, and you're left with an x minus 6 as the only factor left up there. Okay. This becomes very tedious to multiply everything out. There is another method that works very well when you have linear factors. It doesn't work so well if you have quadratic factors. We'll talk about those later. But if you have linear factors, there's something that will work that's a little bit faster. We need to know that traditional technique because it's the only way to deal with quadratic factors. But if we have linear factors, we can do this clever little trick. This equation is true for every single x. If you plug in x, this equation is just true. So if you plug in x equals 0, it's true. It creates some equation that's true. If you plug in x equals 5, if you plug in x equals 1. This technique is called the convenient value method. And so if this is true, no matter what, we can pick some convenient values that will reduce this system. So this is what I mean. When I look up here, a convenient x value to plug in here would be -2, because this would be 0, this would be 0. Another convenient x value would be 6. If we plugged in 6, this would be gone and this would be gone. So we can pick, and if we have 3 denominators, we need to pick 3 convenient values. 2 of them are obvious. We can pick the -2 and the +6. So I'm going to pick x equals -2, and I'm going to pick x equals 6. But I need to pick one more. So these are called convenient values. We can pick anything, but we want to pick something that helps us, reduces the algebra. So we want to pick something probably close to 0. We could pick 1 or -1. -1 would make this turn into a 1, which is an easy number. We could even pick 0. If we pick 0, this side would become 0. Doesn't matter. Any number whatsoever will work. I'm going to pick -1.
Why do we have to choose 3? Is it because there's an A, B,
Because
C?
if we think back to algebra, if there's 3 equations with 3 unknowns, or if there's 3 unknowns, you need 3 equations to solve for those 3 unknowns. If you have 2 unknowns, you need 2 equations. If you have 4 unknowns, you need 4 equations. So here we have 3 unknowns, the A, B, and the C, so we need 3 equations. And let's look at what these equations will now become. Negative 2 across the board. On the left side, we get 64. Negative 2 squared is 4. 4 times 16, 64. Negative 2 here, 0. Negative 2 here, 0. Negative 2 there, we get negative 8c. That allows us to solve for c. Now we plug in 6. On the left, we're going to have 16 times 36. Let's just see if maybe we get some simplification and we don't have to multiply it out. Plug in 6 here, 8 squared, so we get 64a. Plug in 6 here, 0. Plug in 6 there, 0. And yeah, we do. We get some cancellation. 16 will go into there once, and 16 will go into there 4 times. And then 4 goes into 4 once, and 4 goes into there 9 times. So we're going to get that A is equal to 9. Then we plug in negative 1. On the left, we get 16. Negative 1 squared is 1. Here, we're going to get 1 squared, which is 1, so we're going to get A, plus, plugging in negative 1 here, we have negative 7 times 1, so that's going to be negative 7b. Plug in negative 1 here, negative 7c. We've already solved for c and a. So 16 will equal a minus 7b minus 7c. So c is negative 8. So we multiply negative 7 times negative 8 and get 56, plus 56. And then we'll put 7b on the left. So 7b will be 65 minus 16. (65 minus 16 is, what is it, 49? 40 what?
49.
49, okay, thank you. So that tells us that b is 7. So now we have all the coefficients. So let's take our 10-minute break now, and we'll finish this one up after we get back from the break.
I'm not judgmental. I know it's chatting.
Okay, so hopefully this is fast now. Did anyone have a question on how we got to this place where we found a, b, and c? Once we have the a, b, and the c, then we go ahead and we convert our integral into the integral of hopefully much easier things. So our integral, if we want to call it something, we can call it like the fun letter, gamma. So our integral is now, let's see. So a over x minus 6. What's a? I can't even find it. 9, thank you. 9 over x minus 6. And then b is 7, so 7 over x plus 2. And then c, negative 8. So it's over x plus 2 squared. We're going to rewrite that so that we can integrate it with the power rule. So we'll write it this way. So then our answer will be 9 ln plus 7 ln. And then the last term, we add 1 to the exponent, which gives us negative 1. We divide by -1, so that gives us +8. So add, get -1, divide by -1. And then we also have to divide by the derivative of the inside, but the derivative of the inside is just 1. So this is going to turn into 1 over x plus 2, which we could write as 8 over x plus 2. Plus c. I think you're ready. So you all try this one. How many partial fractions are you going to have? One for each power. So you'll have one for x minus 2 to the 1, x minus 2 to the 2, and x minus 2 to the 3. So you have one for each power. All right, see if you can do it.
I'm gonna get 12 from this. 3 is -4. 4. It's like, well, they're not right, so. Let's go outside. 12.
You could do convenient value, or you could do traditional.
Oh, this isn't.
This is traditional. I'm doing traditional here just for heck. You can do either though.
Well,
We can check them both.
well, the convenience only has one convenience.
There's only one true convenient.
Yeah, so,
So then you have to pick two over randomly.
those kind of get, mixed up. Like you could also value.
So if you pick 2, then another good one to pick would be 3, because 3 minus 2 is 1.
I think of that.
Yeah. Make sense?
Oh, yeah, it's probably going to be real.
No, I was right.
Okay, yeah.
That's why.
Okay, well, then that should be.
Why is that minus?
You subtract 4, you get 5.
Oh, thank you. So 0 minus 2. That's included. Plug in 2. Yeah, that's right.
And 1
Figure it out.
equals
A.
minus B.
Yeah, that's good.
I was trying to figure out what you need to
So once you
Why not?
press C, yeah, now you're just going to be plugging it in. You might have to create 2 equations with 2 unknowns.
You could just plug it in, so I tried solving that value plugins and it's like 0 using these 4 A's.
You only have that one in the bottom.
Yeah.
No, you did say that. You read it.
But you don't want to add them until they cancel. Listen carefully. I know I forgot my glasses. Yeah, you don't want to add them there.
Oh, no.
Yeah. You only want to add them once these are the A's will cancel. So you want to multiply one of the equations by a constant so that when you add the 2 together, you get a 0. Right?
I don't remember how to do this.
So I'm just going to line this up with traditional method first, then we can go convenient value method also if everybody wants. Did anyone get A is 1? Yeah. So if A is 1, did anyone get B is 4?
Yeah.
And then C, you got C as what? You got C as 0?
Yeah,
So 4 minus 8, I'm getting 4?
Yeah, I got 4.
Okay.
yeah.
You actually know what's happening? So I'm going to give the name something for the integral, call it omega, call it I, whatever you want. So B we got to be 4. C we got to be 4 also. So there's the integral after plugging in the constants. And with these denominators with the square and the cube, it's easiest to bring those up so that you can use the power rule. So we will end up with natural log, and then minus 4 over x minus 2.
So
Here we add 1 to get negative 2, divide by negative 2, so we're going to get negative 2 over x minus 2 squared plus c.
Yep, and then we'll distribute it to each term. This is going to be the only term. And then we'll still show
It all makes sense now.
4 plus b is 0.
So convenient.
This here is c.
11 a.m. on a Thursday, it all makes sense.
When I did this,
And we just got to get them.
Is everyone okay with the integration? All right. Let's go to the irreducible. So there's a theorem called the fundamental theorem of algebra. And the fundamental theorem of algebra says that you can factor any polynomial into a product of linears and irreducible quadratics. So an irreducible quadratic is a quadratic that has imaginary solutions. So you can't factor it into like x minus 2 and x plus 3 because that has real solutions. So classic irreducible quadratic is x squared plus 1. Right? X squared plus 1 can't be factored unless you use imaginary numbers, which we don't want to do. So note, these are sort of classic irreducible quadratics. So when we do our factorization of the denominator, we're always going to end up with, if we factor as far as possible, linear and irreducible quadratic. Those are the only two types that we can end up with. Now, we already know what to do if it's linear. If we have a linear factor, we put a constant in the numerator to build our partial fraction. If it's an irreducible quadratic, instead of putting a constant up top, you put a linear function up top. So you're always going to put 1 less than whatever the power of the denominator is. So if the denominator was an x minus 2, we put an a. So it's 1 less. So we're kind of building the biggest possible proper fraction. So we can build on top of the quadratic up to a linear. So that's the biggest possible proper fraction. So here's an example. This is an irreducible quadratic. How do you know if something's irreducible? How do you know that you just didn't find the factorization?
You can't make it into a perfect square.
So you won't be able to make it to a perfect square. That's true. But there's some that aren't perfect squares that are still factorable. If you think back to the quadratic formula, what was it that led you to imaginary solutions?
taking the square root of a negative number.
So if you had the b squared minus 4ac, that was the part of the quadratic formula inside the square root. If b squared minus 4ac is negative, then you know you have an irreducible quadratic. So if you want to confirm that this is irreducible, you could check. You could do b squared minus 4ac. b is the coefficient of x. A is coefficient of x squared. C is the constant. So minus 4 times a is 1. C is 2. So this tells us that it's irreducible. So if the b squared minus 4ac is negative, you've got an irreducible quadratic. And it's not that you just didn't find the factors. It's that they don't exist. So here, we'll take our inside. And we're going to rewrite it as a over x. So there's the linear factor. And then this is an irreducible quadratic. So we have to have a linear expression in the numerator of that. So that will be our setup. And if that irreducible quadratic happened to be cubed, you would end up with 2 extra factors, another one for this squared and another one for this cubed. So the same pattern that we did for the linears. You would have to have a fraction for every power of the factor. Okay. Now, we clear the fractions. So we multiply both sides by this denominator on the left. When that denominator multiplies to this fraction, the x's cancel. So we'll have a multiplied by this. When that denominator multiplies to this fraction, we'll end up with bx plus c times x. Because this denominator will cancel with that denominator. When you have irreducible quadratics, most of the time you want to use the traditional method. Most of the time. We could commingle the methods because there is a very convenient value of 0, which would help. So you can sometimes mix the methods if you want. I'm just going to go traditional method here, though. So we distribute the A, distribute the x, and then we're going to set up our system. So coefficient of x over here, of x squared, is 1. Coefficient of x squared over here is a plus b. Coefficient of x on the left is 3. Coefficient of x on the right is 2a plus c. Space out the c and try to create columns. And then constant on the left is 2. Constant on the right, oh, it's just that one. Okay, that's easy. So 2 equals 2a. So this tells us that a is equal to 1. And if a is 1, b is 0. And if a is 1, c is also 1. So that would be our set of solutions.
Where did we get like 1 is a plus b? Where'd that 1 come from?
So that is the coefficient of x squared.
Okay, right.
So this coefficient is 1
Right.
right there. That's not looking very good, but that. So that matches the a plus b. Everyone seen how we got all those equations? And so then we're at the place where, hopefully, we can integrate. So this gives us, if we call this integral something, omega, call it whatever you want. So we're going to have a divided by x. And we found a to be 1. So 1 over x. b is 0. That's convenient. And then c over this thing. Now that denominator, the second denominator, does that factor?
We can make it log form.
Well, we cannot make it log form actually because this is power 2. So what's its derivative? 2x. And is there an x up there?
Oh, I see what you're saying.
Yeah, so there's no x, so we can't make it log form. But what about, does it factor? Does that denominator factor?
We split the fraction?
Well, that's a good thought, but we can't split it because the bottom has 3. So typically when we split, we have the top have 3 and the bottom has 1, then we can share it. What does that factor into? X plus 1 squared? That is a perfect square trinomial, right? It's a perfect square trinomial, so it's going to factor into x plus 1 squared. And so that allows us to pull it up to the numerator with a -2. So all those techniques that were mentioned are absolutely things we want to be thinking about. And everyone's clear why this is not in log form? Because there's no x up there. If there's no x when we have a quadratic in the bottom, we can't make it in log form. Katie?
I might just be really tired, but how does that factor to x plus 1 squared?
If we do x plus 1, I'm really tired also, so let's check. Let's check. So if we do first, we get x squared. Outer, we get x. Inner, we get x. And last, we get 1. So x squared plus 2x plus. Oh!
Yeah. I was looking, it's identical to the top one, which we already decided was.
Oh my god. Where's my pillow? Okay, that's why you were thinking of all those other techniques, because it doesn't factor. That doesn't factor. Thank you. Oh man. What do we do if it doesn't factor?
Complete the square.
Complete the square. Yes. And then maybe we can put it in log form. Who knows? Let's see. Oh, my head. Oh, we still can't put it in log form, but does everybody agree that that's how we would factor it with completing the square? Because x plus 1 quantity squared we just saw would be x squared plus 2x plus 1, and then we have an extra plus 1. And what form is that in?
Arctangent.
Arctangent. Oh, yes, yes, yes. It takes a village to integrate. Do we have to deal with any reverse chain rules business there?
No.
No, because the derivative of that parenthetical piece is 1. Oh. Getting delirious.
Let's just call it a day.
No, not yet. We'll call it a day soon. I gotta make it 30 more minutes. I don't want you to get behind. I'm here for you. Okay. All right, you all start this one then. So this is the worst possible scenario that I would ever ask you to try to do by hand. Yeah, you're so confident. I have complete faith. So 2 irreducible quadratics. I'll never ask you to do worse than this. That I remember.
We go back to Calc 1.
Whoa.
Whoa.
So there's the basic setup. So run with it, little lambs.
Yeah, the x would be a y, right? The cx, cy.
Thank you.
That's a sign. Everybody more words.
What are we talking about? It's AY plus B, the whole thing. You have to FOIL. It's supposed to make a full system. B plus D is 0. Is 1, and D is negative. Two systems is 0. I don't know. I just AYQ plus 2 plus B minus 3. That's just A plus CYQ plus C plus BY squared. Well, we have two x cubed terms. Put them together. We can get x cubed is equals 0. If we think about, because we're solving for the other side of the equation, which is 0x cubed plus 0x squared equals 0x plus 1. We almost just did that. This is what we did. So really,
Did you all get that system?
After looking at the board, yes.
So eventually? So from here, you're going to pair off your equations. Pair off the equations.
these are my systems.
So I'm going to do the red. I'll subtract the two. You could subtract the reds in either order because they both have A and C. So I'm going to do equation 3 minus equation 1. So 3 minus 1 is going to be 0. 2A minus A is A. C minus C is 0.
Why isn't B plus D 2?
B plus D. So
Because that's y squared.
y squared, there's no y squared over here. Or
But
don't,
if we FOIL it out, there is a y squared.
we have y squared on the right, but on the left side, the numerator is the left side.
A plus C equals 0, B plus D.
Do you know what I'm saying? Like the left side is this. When we multiply by this denominator, the only thing that's left is the 1.
Oh,
Yeah.
I see.
You see it?
Yeah.
So this is 0.
B plus D equals 2B plus D.
Alright.
So we could do that.
Okay, thank you.
Yeah.
A is negative 1.
And then with the last one, let's do
Plus negative
number 4 minus number 2.
I'm not there yet. Just watch. He's
So 1. So if A is 0, C is 0. And if B is 1, if B is 1, D is negative 1? So that's the worst system we're going to have to deal with in this class. So then our integral, call it omega or whatever, is going to be the integral of ay plus b. So 1 over y squared plus 1. And then c is 0, d is negative 1, so negative. There we go. And what's the first one? Arctan? The second one's also an arctan, but we have to do a little bit of work. So this is going to be arctan of y minus, here we're going to factor out a c, or factor out a 2. So I'm factoring out a 2. And then we need to write this as a square plus 1. And what is the square going to be?
X over 2y.
Yes. But y? Y over root 2. Right? So the parts that are left over here, we have the y squared and we have the 2. And we want to write that as a single square. So to write that as a single square, that denominator is not a perfect square, so we'll just use the square root of it. Now we're good-ish. So negative 1/2, space for RCR, the RCR gap. And what goes in our RCR gap? So we're going to multiply by the reciprocal of the derivative. The derivative of this is 1 divided by root 2. Dividing 1 divided by root 2, we multiply it by root 2 over 1. So not anything we can really do to simplify. These arctangents cannot be combined. So that's where we're at. All right, any questions on any step there? Anything
The key
causing a perturbance in the force?
be very confident in your boiler and solve for like terms.
Okay.
Find your like terms. And then you have to think about the equation. You have to imagine it's a bunch of zeros.
All right, you all. Find the area of that region. Let's go. Find the area of that region. This is not a graph you need to know, but you do need to know how to graph an exponential function, e to the x. But this is not e to the x, so it's
Never mind.
given to you.
A plus 0 equals 0, so A equals 0. And then 0 plus
So
C equals just.
This is a contrived application.
There you go. So now you've solved.
We just want to integrate using PFD.
But it's
There are only two here.
Yeah, we sure you want that day. That's Tuesday. Wednesday and Thursday.
So this is real. At first I thought it was like a volume problem.
Now it's all this.
No.
We need quadruplets.
I just like use the same pictures when it's not
Remember the
volume.
one? Yeah. We need quadruplets. Yeah, and so
Did they all
you
live?
couldn't escape them. You couldn't escape them on there.
Somewhat,
Only
yeah.
one, at least one.
Sounds like a,
Sarah.
one of those reasonable work rides things. Haunted house.
They never see my hair when they use those tall parts.
They just have numbers on it for it.
Yeah, one dude was named Guy, I think they like and they got to the first one.
They were all,
No gap right here. This is a irreducible
There's a really.
polynomial. So whenever you have a irreducible
Our school is
or
twins that.
value on top that's going to be in the form of a linear equation because it's
what school is that?
always. Yep, that's just. It's because you can
There's
introduce.
water down there.
She's hot, it's crazy hours. I live just go.
Yeah, exactly. You just have to know that that is always true.
So there's the equation you should get to. And then, should we do some commingling this time? Mingle the methods? Let's do it. Let's mingle the methods. What is the convenient value that jumps out at us? The convenient value that jumps out at us is -1, right? Right? Don't listen to those twins. Okay, so if we're going to mingle the methods, first we're going to plug in a convenient value from that linear factor. And if we plug that in, let's see what we get. So -1 over here, so we get -1 minus 1, so we get -2. And then we get 2 times a. And then over here we get 0. So this gives us that a is -1. Do we all agree with that? So here's how we're going to mingle the methods. Now we plug the a value back in. So we're going to plug it in right there. And that's going to give us -x squared minus 1 plus, and over here I'll FOIL this mess out.
can actually start.
And what do you think we're going to do with the negative x squared minus 1?
For A. But yes, that is right.
Should we move it somewhere? Move it to the left side. Great. Because there's no B's or C's in this, right? There's no letters, so these can combine with the other side. Oh, don't we get a cancellation? Right, those add to 0. So the left side becomes x plus 1. And then the right-hand side, looks like that. So what does b have to be? What is the coefficient of x squared on the left? 0. Coefficient of x on the left?
C has to be 1.
1. So coefficient of x is b plus c. Constant is c. So we get that b is 0 and c is 1. So now we have all our constants. So the integral right here can be rewritten 0 to 1. And I forget what the constants are already. A is negative 1. Negative 1 over x plus 1. And then bx plus c. So 0x plus 1. So 1. Does that look right? Did I plug it in properly? I can't tell. So these are easily integrable. So we get minus ln absolute x plus 1 plus the arctangent of x from 0 to 1. Plugging in 1, you get minus natural log of 2 plus arctan of 1. And what happens when we plug in 0? Does that give us anything? Natural log of 1 is 0. Arctangent of 0 is 0. Exactly. Everyone's right on track. So we have this. Now, could we simplify this one term? Can we simplify that term?
Like pi over 4.
Pi over 4. So this, I shouldn't actually put the box around that one above it because we definitely need to simplify that. So let's put it there. There's only one arctan value we know well, and it's that one. We know some other ones a little less well, but that one we know well. And that better be a positive number. Pi over 4 is about 3/4. Natural log of 2 is something like 0.7 or something. 0.8. So it will be positive. Will be positive. Negative natural. Natural log of 2 is less than 1. Oh, yeah. Somebody type in, what is natural log of 2?
0.693.
0.06?
No, 0.693.
0.6, so 0.7.
Yeah.
And this is a little more than 0.75, so it will be positive. But pretty small area. Looks like it should be bigger. Oh, I guess that's 0.2.
That makes sense.
Okay. All right. Gotta look at all the numbers. All the numbers. Okay. Find the volume. We're going to rotate this region around the x-axis from -1 to 1. So what technique do you think we'll use? Which method? Did you say a method?
No,
Oh.
I didn't say anything.
You said nothing. I'm hearing things also. I'm definitely seeing things because
Guys want to go like the washer method? I think that's good.
you're done. Is that what you said?
Yeah, yeah.
So this is rotating around the x-axis and it's touching the x-axis. So could we possibly get a washer? No, we can't get a washer because it's touching the axis of rotation. So we're going to get a disc. We're going to get a disc. So we're going to take our vertical element right there, vertical element at x. So that rotates around the x-axis and it creates kind of a spool-looking thing. And the radius of the disc, the radius is right here. The radius is coming from that function that builds that curve. So anytime we find the volume of a solid of revolution, we first find the area of the cross-section. So this is going to be the area of a disk. Area of a disk is pi r squared. And the radius is given by the function. So the function squared is going to give us something pretty straightforward. Look at that. So that's the area of the disk at x. So if you plug in 0, you're going to get the area right there. Plug in 1, you're going to get the area over there. So how do we find volume from area? Integrate. If we have cross-sectional area, we integrate that to get the volume. So we're going to integrate the cross-sectional area. Now, is there some symmetry that we could go with here?
Yeah.
For sure. So if we go from 0 to 1 and double it. So we'll go 0 to 1 and double. So the 2 out in front is the symmetry piece. Now, that denominator can factor. We have been dealing with descending powers of x, which is what I would recommend doing. Whenever we factor, it's usually easiest if the x squared is positive. So why don't we pull that negative sign out to the front? So let's go ahead and pop that negative out to the front, giving us -2, 0 to 1. Oh, and the pi. Let's pull the pi out. So we have bx over, if we factor out that -1, we'll have x squared minus 4. That's a better way to factor. All right, so then we factor it. Because this is factorable. I'm confident. That's factorable. Difference of squares. Now, this is a stage where you could use a different technique.
I was gonna say, can't we just?
Use trig sub, right? We could use trig sub. This is a difference of squares with a trailing 1 if we factor out the 4. And what substitution would we use? Sine, secant, or tangent for this one? What was that? No. Secant. Because remember that if it's, remember it has to be an identity. So with this right here,
Shouldn't our 1 be leading?
say that again?
I'm sorry, from the first part to the second part, the 4 was in the front.
The 4 was in the front?
In the denominator?
You took out the -1 to switch to x squared.
Yes, so I,
Oh, okay.
you see it? Yeah, so I factored out that -1 to make that -2. And then that switched the 2.
Okay, thank you.
Yeah, sure. And so then here, so I guess this is a good point actually. So if we're looking at this one, it's going to be secant if we factor out the 4. But if we factored out the 4 there, we would use
Sine.
sine. Yeah. So we could use either of those in that case. Now, most people, given the option of PFD or trig sub, most people are going to pick PFD. PFD is going to be a little easier. But you could certainly do trig sub here and see if you get the same answer. So we'll do it trig subs, PFD, since that's where the section we're in. So we'll PFD it. And PFD with two linear factors is pretty fast. So we've got that. We multiply both sides by the denominator that's on the left. We get that. And because you are now masters of PFD, that's really easy with the convenient value method if we know how to pick convenient values. So what are the two best convenient values here?
2 and -2.
2 and -2. Is that what you were going to say?
Yep.
Good. Good. Everyone's on track. No distractions here. Plugging in 2 is going to give us 4a. Plugging in -2 is going to give us -4b. So we get that a is a fourth. We get that b is -1/4. And that will allow us to rewrite this integrand as a over x minus 2, and then b over x plus 2. And that's it's very easy. Log form. So we'll factor out the 1/4 and get -pi/2. So we'll factor this to the front and combine those. And then the integral of x minus 2 in the denominator, natural log, absolute, x minus 2. So we get that. And we're almost there. So let's see. Plug in 1. Natural log of -1 in absolute value means natural log of 1, which is 0. If we plug in 1 there, we get 0. So we get 0 minus natural log of 3. That's for the upper limit. If we plug in the lower limit, we get natural log of 2 minus natural log of 2. Are we jamming with this? So we get pi ln 3 all divided by 2. Right, John? Do we agree? Yeah. Okay. Done. I'll be better on Tuesday, I promise. Any questions on that one?
Will we see one that we need to calculate volume on the exam?
I can't think clearly right now, so I'll get back to you on that.
Okay. I'll look at your former tests.
Exactly. We'll talk about it next time.
I tried to teach matrix at 1.1. Yeah, I
Did it
know.
get messy?
It got really messy. I had the integral of cosecant.
Had a lot of them.
Okay, well, that's similar to secant.
The
Yeah.
problem is I don't know, like,
I'm just like,
there's one that's like
Yeah,
this.
PFD is always going to be a little easier. PFD is easier. All right, so today I'm not going to do office hours. I feel like crap, so I'm going to go lie down. Try to recover
What did you get?
from this terrible sore throat.
To a school?
Have a good weekend, everybody.
It's like high school freshman year where you're just allowed to leave the building.